Welcome to my YouTube channel Modi Mechanical Engineering Tutorials. So in this video I would like to draw, or you can say construct, a phase diagram for hypothetical binary systems of a component A and B. So first of all, starting with the melting point of A and melting point of B. So melting point of A, that will be 1400 degrees centigrade, and melting point of B, that will be 1960 degree centigrade. So here it will be the eutectic temperature 1150 degree centigrade and eutectic compositions 45% of A and 55% of B. Some more relations it will be given like this. So here at a temperature around eutectic, so at TE temperature, and that will be 1150 degree centigrade, so solubility of B metal into A, solubility of B metal into A, that will be 16%, and solubility of A into B, that will be 11%. Now second conditions at room temperature. So once again, solubility of B into A and A into B. Room temperature, solubility of B into A, that will be 2%, and A into B, that will be 0.2%. So this is an example of both the metals which will be having a 100% solubility into liquid state, but that will be having a partially solubility into solid state according to the given compositions and the different temperature range. So sometimes it will be forms a single solids, and rest of the others it will be, you can say that technically it will be the partially solubility into solid states. So let's see and draw the diagram for these hypothetical binary systems of A and B. So after making an x-axis and y-axis, just you can make x-axis as a weight percentage of composition, and here it will be the weight percentage of A metal and weight percentage of B, and this y-axis, that will be the representation of temperature in degree centigrade. Now I would like to make a parts onto the weight percentage of composition line with respect to the different weight percentage of A and B. So just you can see. So onto x-axis, that will be the 100% of A onto the left side, and other side it will be the 100% of the B, and that will be the fraction of the 10% of A and B. So it will be the 90-10, 80-20, and likewise this. And onto the temperature axis, it will be according to the given range of the temperature, or you can say highest temperature around 1960 degrees centigrade. So maximum limit it will be up to the 2000. So 400, 800, 1200, 1600, and 2000s. Now I am interested to making a different point according to the melting point of A and B. So starting with the melting point of A. So just you can take a point at 100% of a material, so which will be act as a pure metal. So here that will be the point of 100% of A, and according to its melting point. So for the pure metal it will be same as a freezing point, right? So 1400. So just you can make a point in between these two. So 1400 degrees centigrade, that will be from the melting point of A. Similarly from the melting point of B. So here it will be the 100% of the B, and it will be around 1960. So almost it will be just below of this. So it will be 1960 degree. Now according to the given conditions, or you can say the eutectic conditions, so eutectic temperature it will be 1150. So just you can make a point at 1150. So almost it will be around this point. So that will be the eutectic temperature and eutectic composition. So 45% of A. So it will be over here, 45% of A. So now I would like to make one vertical line from the composition line and one horizontal line from the eutectic temperature line. So here it will be the eutectic temperature, and this point it will be representing as a eutectic composition. So by the making of one vertical line and horizontal line, it will be intersecting is this point. So that will be known as a eutectic point. Liquid phase of any metal, here it will be A and B, that will be transferring by the cooling into the two different solids. So here it will be the S1 and S2, or you can say alpha, or you can say beta. So that will be the two solid phase is being formed by the eutectic reactions. Once again, by the heating it will be converting into the liquid form. So here it will be the 100% liquid that will be converting into two different solids. So this is a eutectic reactions. So generally it will be take place at a eutectic temperature and eutectic compositions. But here it will be the case of the partially eutectic system. So up to this it will be the similar kind of diagram as we already discussing into the last video. So for that you will find a link in my description box. So right now it will be some more conditions it will be given like this. So at an temperature, or you can say at eutectic temperature, the solubility of B into A it will be the 16%, and solubility of A into B it will be the 11%. So just you can see. So now at left side, or you can say at 100% of A. So by the moving by these directions, it will be the B will be added into the A. So this is the side of the solubility of B into A. So according to this, at a temperature of eutectic, so this temperature, solubility of B into A, so 16%. So it will be the point of the 16% of B into A. So just you can make a one point. So that will be representing as a 16% of B. Similarly from another end, A it will be having a solubility into B, it will be 11%. So from this side it will be the 11% of A at a temperature range of eutectic. So just you can make a point with respect to this temperature and this solubility. So here it will be the 11% of A. So 2 point it will be identifying. Similarly at room temperature, so just you can make a one point around room temperature. So room temperature, so B into A 2%, so it will be around this 2% of B, and A into B it will be 0.2%. So it will be around this 0.2%. So according to the eutectic point, here it will be the first point from the melting point of A, so that will be P. Eutectic point it will be Q, and from this side, or you can say melting point of B, so it will be R. So now I would like to join these 3 points, P, Q and R. It will be act as a liquidous line. Now according to the solubility at different temperature with B metal into A and A metal into B, so these points, so I would like to join like this. So just you can see this line, or you can say I would like to make a point S and T. So this line, just you can see P, S Q, T and R. So this one is act as a solidus line, and this line as to the room temperature. So these two lines, it will be known as solvus line. So as we are discussing, at above portion of the liquidus line, so it always forms a 100% liquid for any compositions of A and B, and just below of the eutectic transformation line, so it forms a two solids. So here it will be the point of a eutectic, so S1, so that will be nothing but alpha plus S2, so that will be nothing but beta. Now according to the given condition of the solubility with B into A and A into B with the different temperatures, so just you can make this region. So here it will be having a solubility, and rest of the others from the S point to the T point up to the room temperature, it will be act as a totally insoluble, because that will be the around region of the eutectic. So in the case of the eutectic, it always forms a two solid, but this diagram, it will be related with the partially solubility. So both the metals A and B, which will be having a different condition with respect to the different set of conditions of the temperature and compositions. So according to this point of S and T, that will be having a solubility. So from both the end, from left side and right side, so which will be having a solubility region. So just you can make a hatching line, so that will be shown the solubility region for A and B according to the given conditions. Suppose from left side, so just you can see that will be the majority of the metal A, it will be present. So that metal A, it will be the first to form a single solid, because that will be having a 100% solubility up to these regions. So this area, it will be having a total solubility into solute state from the both the ends. So from this side, solubility of B into A, so it will be forms a single solid. So that solid, it will be refers to the enrichment of the metal. So here it will be the majority of the A, so it will be forms alpha phase. Similar way, from the another side, this is the side of the majority of the B per metals. So according to the presence of the B, it will be forms a single solid up to the set of conditions of the temperature and compositions. So it forms a single solid. So that will be the phase as a beta phase, and in between S point to T point. So just you can see, so just below the eutectic line and in between these two lines, it will be act as a totally insolubles. So it will be forms alpha plus beta from both the sides. Now this is a eutectic transformation line. So before any point of the compositions, it will be forms a hypoeutectic transformations. Just you can note down. And after the eutectic line, it will be makes a hypereutectic transformation. Now I would like to talking about in the region of hypoeutectic transformation line. So basically, according to the rate percentage of A and B, so once it will be crossed the liquidus line, so it will be the starting point of the solidification process. So here it will be the liquid plus alpha, or you can say A, because A metal, that will be the first to form a alpha solid phase, because that will be depends upon the enrichment of the metal. So here it will be the majority of the A. Similar way, it will be liquid plus beta. So just you can see the different phases. Above the liquidus line, it will be always makes 100% liquid. Just below the liquidus lines, it will be forms a liquid plus alpha as a solid, so two phase. From other side, it will be liquid plus beta, so two phase. and just below the eutectic temperature line in between S point to T point, it will be act as a insoluble solid solution. So it will be having a two different solid phase of alpha and beta, and according to the solubility of B into A and A into B at a different temperature range, it will be makes a single phase. So here from this side it will be the single phase alpha, and from this side it will be the single phase beta. Now I would like to take different points onto the composition line and explain how the transformation from the 100% liquid to the room temperature. So let us start with alloy number 1 with compositions around 1.5% of B. It will be present into the A. So just you can make a one vertical line. So by the making a one vertical line, so just you can make different points. So that will be the A point intersecting at a liquidous line, so B point. Once again it will be intersecting at C point and around a room temperature. So these all are the transformation points where the 100% liquid, it will be transforming into different phases and up to the room temperature. So let's see. Just you can see at point number A that will be having around 99% of A. So the majority of the A, it will be in the form of the liquid phase, and rest of the other as a metal B, it will be in the form of liquid state. So which will be forms 100% liquid of A and B at point number A. But what happened at point number B, just you can see, so that will be touches the liquidous line. So it always start to solidify, but the majority of the metals, it will be solidified first. So here it will be the site of 100% of A. So now this liquid of A and B, it will be converting into liquid plus alpha at point number B. So this will be the region of liquid plus solid, or you can say liquid plus alpha. So now you will see the microstructure at point B. So at point number B, it will be the starting of the solidifications, and most of the tiny particles, or you can say nuclei, that will be from the metal A. So that will be the nuclei, and rest of the others of the metal A as well as metal B, it will be in the form of liquid. So just you can see, so this nuclei, it will be from A materials, and which will be found a alpha phase. So it will be the starting point of the solidification process, and it will be forms a alpha phase as a solid particles from metal A. So this is a microstructure of B. Now I would like to interest to draw a microstructure at point C. So when transformation line, it will be touches the solidus line. So this C point, it will be onto the solidus lines. So we all know onto the solidus lines, all the compositions which will be present into the liquid or solid phase, it will be transforming into 100% solid. So just you can see, and according to the solubility of B into A and A into B, so this is a region, so it will be having 100% solubility into solid state. So it will be only forms a alpha phase, because that will be the enrichment of the metal A, and which will be forms a alpha phase. So here it will be the only forms a alpha. So that will be the single phase solid. It will be present at point C, and at your room temperatures, which will be having a rearrangement of this alpha phase. So just you can see at a room temperature. So the important thing for this alloy, or you can say alloy number 1, so which will be in the region of the 100% solubility into the liquid state as well as into the solid state. So which will be forms a single phase solid as a alpha. Similar, you will also take the regions from the another side for a single phase beta, because there will be the enrichment by the metal B. Now I would like to make a different alloys for eutectic as well as hypoeutectic or in the case of hyper-eutectic region. So let's take a second alloy which will be around a 70% of A and 30% of B. So this point. So just make a one vertical line, so that will be representing as a transformation line from the liquid to the solid. So after making a one vertical lines from 70% A and 30% B, so that will be alloy 2. So which will be intersecting at the different points. So here it will be onto the liquidus lines and onto the solidus lines, or you can say eutectic temperature line. So I would like to make a different points like A dash, B dash, C dash, and at room temperature that will be T dash. Now making a microstructure at a different point as a dash, so that will be above the liquidus lines, so it will be forms 100% liquid. So as you can see, so at A dash with the 70% of A and 30% of B, so it will be makes 100% liquid. But here it will be the 70% A and 30% B is present. So the proportion is around 70 to 30 with A and B. But it forms 100% liquid phase of A and B. But I am interested to talking about B dash point and C dash points. So now B dash point, that will be representing as a intersecting point onto the liquidus line. So once again, which will be intersecting the liquidus line, so that will be the starting point of the solidification process. So according to the phase diagram, so this liquid phase of A and B, which will be transferring into the solid. So this is a region of eutectic binary alloy. So it always forms a liquid plus solids. So if you want to make a cooling curve, so just you can see, so above the liquidus lines it forms a liquid. After B dash point it will be having a liquid plus solid. So here it will be a solid as a alpha phase, and in between these 2 points which will be onto the eutectic temperature line, or you can say constant temperature line. So it will be having a 3 different phases like liquid plus solid 1 plus solid 2. Here solid 1 as a alpha and solid 2 as a beta. So here it will be the liquid plus alpha plus beta, and after, or you can say below the solidus lines, it forms 2 different solids. So S1 plus S2. So here S1 as a alpha and S2 as a beta. So below this eutectic temperature line, it forms 2 different solid as alpha plus beta, because both the metals that will be having a insoluble in these regions. So now just you can see the microstructure at B dash point. So at B dash point, the majority of the metals which will be present, so it will be having a starting point of the solidification process. So from hypo, so that will be the majority of metal A. So that will be forms a alpha phase as a solid. So that will be the alpha phase, and most of the others it will be still into the liquid phase. So here it will be the alpha phase, which will be represented as a solid tiny particles of metal A, and rest of the other as a liquid. Now at C dash point, so just you can see over here, so just below the eutectic temperature line, it completes the solidification process. So it will be makes 2 different solids as alpha and beta. So just you can see, so this alpha beta, alpha beta. So just below the eutectic, it forms alpha plus beta structure, which will be insoluble at solid state. So this is a theory about second alloy, which is into the hypo-eutectic transformations. Now this will be the important, and that will be the eutectic. So alloy 3. So alloy 3, or you can say eutectic transformation, for partially solubility. So just you can see just above this point it will be forms a 100% liquid, and onto the single temperature or single point which will be transforming into two different solid as a S1 and S2, or you can say alpha plus beta. So that will be nothing but the eutectic mixture of A and B, or you can say alpha and beta. So I would like to make a microstructure for A double dash and B double dash. So here it will be the around room temperature. So just you can see the microstructure at just above a eutectic temperature. So just above the eutectic, so it always forms a 100% liquid, but here it will be the eutectic mixture, or that will be 45% of A and 55% of B. So here it will be the A, it will be in the liquid form, and B, that will be also into the liquid form. So it makes 100% liquid at above the eutectic temperature line. After the eutectic temperature line, it converts into the two different solid, because we already discussing the eutectic reactions. So 100% liquid by the cooling at eutectic temperature and eutectic compositions into two different solids. So here it will be the alpha plus beta. Now I would like to draw a microstructure for alpha and beta. So at room temperature, the alpha and beta, it will be into the laminar layers, but that will be separated by each other, because both the alpha and beta, that will be insoluble with each other. So this transformation take place from the eutectic point. So it will be known as a eutectic transformations. Now I would like to make one more point that will be in the region of the hyper-eutectics. So just you can take around 20% of A and 80% of B. So these points, and making a one vertical line. So let's say, so similarly we already discussing for the alloy number 2. Now this is alloy number 4. So which will be intersecting at a liquidus line, solidus line. So similar way we already discussing into this case. So above this it will be makes a 100% liquid of A and B, but here for the A, that will be the 20% of A and 80% of B. Similarly it will be touches the liquidus line. So it will be the starting point of the solidification process. But here that will be the enrichment of the B metal. So it forms a nuclei that will be from the beta, because that will be the majority of the B metal which will be present for the hyper-eutectic transformations. So for making a microstructure at these points, just you can see. So once it will be touched the liquidus lines, it will be the formation of the solid particles, and the majority that will be from B. So that will be representing as a beta phase, and most of the other beta that will be still into the liquid phase, and up to the 20% of A, it will be in the form of liquid. So from this it will be makes a liquid plus solid regions, and that will be liquid plus beta. But once it touches the solidus lines, so it will be the completion of the solidification process, and this is a region of both the metals which will be insoluble into solid state according to the given condition of the solubility. So which forms two different solids as alpha plus beta. So similar kind of microstructure just we observe over here, but the weight percentage of A and B, or you can say alpha and beta, with different into the manners. So just you can take a microstructure at this point. So here it will be the alpha phase and beta phase, but both the alpha and beta which will be separate out because both are having a insoluble into solid state. But the majority of the beta, because that will be the 80% of the beta, is being present for the hyper-eutectic transformation. Now I would also like to make a relation of the weight percentage of the liquid and solid alpha for a hypo-eutectic transformations. So just you can make this point as a 70% of A and 30% of the B at around 1200 degrees centigrade. So just you will make a one horizontal line which will be passing through the solidus line, composition line and liquidus line. So let's see. So this temperature line, it will be intersecting at a solidus line, composition line and liquidus line. So here it will be the X point onto the composition Y and onto the liquidus Z point. Now I would like to find a weight percentage of liquid for these compositions and temperature range around 1200. So this is calculated by the lever arm rule. And weight percentage of liquid. So for finding the weight percentage of the liquid, so you will take a side where this temperature line, it will be intersecting at a solidus line. So at X point. So this line X, Y and Z, it will be known as a tie line. So for finding the weight percentage of the liquid, just you can take a side from the intersecting from the solidus line. So X to Y divided by total line XZ into 100. Now for finding the distance of X, Y and YZ, so just you can make a projection line onto the composition line. So by the making a projection line from the X, Y and Z, so X almost it will be 8% of B. So I always take a reference as a weight percentage of B. For composition line, that will be the 30% of B, and from Z it will be around 43% of B. So for X to Y, so this much, so 30 minus 8 divided by 43 minus 8 into 100. So around 62.85% of liquid, and remaining portions it will be still into the solids. So if you want to find weight percentage of alpha, so just you can take a side which will be intersecting at liquidus line, so that will be the point Z. So YZ divided by XZ into 100. For YZ it will be 43 minus 30 divided by 43 minus 8 into 100. So it will be almost 37.15% of alpha is being present for the point Y. Similar way you should also find for the in the case of hyper-eutectic with the lever arm rule. So I hope you understand this diagram as both the metals which will be soluble into liquid state but partially soluble into solid states. So if you like this, then subscribe and share more the mechanical engineering tutorials. Thank you so much and keep watching.